The Best of Our Knowledge explores topics on learning, education, and research. Coming up, arsenic is a naturally occurring toxin with a big reputation. But scientists say arsenic-contaminated waste could have a potential public benefit, including in advanced manufacturing. I'm Lucas Willard, host of The Best of Our Knowledge. This is The Best of Our Knowledge. I'm Lucas Willard. Arsenic, the notorious poison of kings and common contaminant, can cause serious health problems. But researchers now say the naturally occurring arsenic could have use in advanced manufacturing, like in the production of high-tech semiconductors. Our guest today is Kees van Genuchten, a senior researcher at the Geological Survey of Denmark and Greenland. Kees is the lead author of a recent study that explores a potential societal value of arsenic. With the assistance of the Canadian Light Source at the University of Saskatchewan, Kees's team found a way to transform arsenic waste into a form that has real economic opportunity. I spoke with him to learn more.
Arsenic is a naturally occurring element that occurs just naturally in the Earth's crust, and where it has really caused a human catastrophe is in areas that rely on groundwater. And that's because arsenic-bearing minerals can make up the groundwater aquifer. And if you have groundwater flowing through an aquifer that has these arsenic-bearing minerals, a little bit of arsenic can leach into the groundwater. The kind of the nefarious thing about arsenic is that it's colorless, it's tasteless, it's odorless, but if you drink groundwater that has even a small concentration of arsenic, if you drink groundwater with that small concentration of arsenic for decades, you end up with cancer. Arsenic poisoning from chronic exposure to arsenic in drinking water, that's something that has affected millions of people's lives, where it tends to have the biggest health impact is in rural areas of Northeast India and Bangladesh. And that's because the naturally occurring arsenic levels in groundwater are so high, just based on parent geology. And you have high population density, and you have very little infrastructure for removing arsenic from groundwater, so arsenic treatment. Now, in general, the way that I think about, or the way that I often talk about arsenic contamination is that it's a global problem. Naturally occurring arsenic is found all over the world. It's just a function of parent geology. And so there's been some very, I'd say, notorious maps of arsenic contamination in groundwaters across the world, and you see hotspots in every inhabited continent. But in terms of the human health toll, arsenic really impacts areas that have poor access to infrastructure and resources the most. And that's because in areas like, where I grew up in California, in the parts of the Central Valley of California, they have naturally occurring arsenic, but there's also centralized drinking water treatment. And so it turns out that arsenic isn't necessarily so difficult to remove from groundwater, so you can produce arsenic safe drinking water. But, and this kind of leads into our recent work, when you remove arsenic from groundwater, you're not converting it into something that's non-toxic. It's still a carcinogen, but you're taking it out of the water and you're concentrating it into a solid form. And now you have this arsenic-rich kind of drinking water treatment waste, and nobody knows what to do with that. And I think it's a really interesting kind of I'd say in the last, 20, 30 years, the environmental science and engineering community has really focused in on arsenic. But when we talk about treatment, it's pretty well understood now how to remove arsenic from groundwater, but very few people have continued to think about what happens after arsenic is removed. And I can talk a lot about what's done currently with this waste, but maybe I'll stop there.
Yeah, let's take a step back for a second. So,
Sure.
when arsenic is removed from groundwater, say
Mm-hmm.
every day at a regular water treatment plant where you and I would
Mm-hmm.
get our tap water, it's
Yep.
removed and it's concentrated into a substance,
Yep.
concentrated arsenic. And
Yep.
what is currently done with it? If nobody wants to touch it,
Yeah.
is it contained somewhere? Is it put into landfills? What
Yeah.
is the problem that this cancer
Yeah.
causing compound can actually what
Yeah.
is the problem with this substance?
Yeah. I wish I could show you some of the pictures I have. So the the short answer to that question is it depends on where you are in the world, because it typically depends on what the local regulatory guidance is. So if you're in an area, I'll give you an example. So I live in Copenhagen now. In Denmark, it's there's several things that are done with this waste. I'd say the best case scenario is you put it into a landfill, and of course that's not a great idea. But you essentially you dig a hole, you put the waste in there, and then you kind of hope that it doesn't make it back into the environment. There's plenty of things that are wrong with landfills, but that's the best case scenario. There are many other kind of like less controlled disposal practices where you can put it into a disposal pond. You can put it directly into the sewer so that it becomes like a wastewater treatment problem. It's stockpiled, and worst case scenario, you take this concentrated arsenic rich waste and you just kind of do open disposal, we call it. You discharge it to surface waters and soils, and that open disposal route is really the worst for human health and the environment, but it doesn't cost anything. And so, kind of anecdotally, that's the most practiced method in areas that don't have resources and infrastructure or space for landfills. So, I mentioned earlier that, in terms of like the global health toll, the like parts of Northeast India and Bangladesh have been hit hardest by naturally occurring arsenic, in part because there's very little resources there. But it's kind of this irony where these are the same communities that need treatment the most, but there's also very little infrastructure for dealing with the waste there. And so that's where you see in these rural areas, that's where you see these open disposal practices that really need to stop. And that's just putting this concentrated arsenic rich waste into soils adjacent to the village. You might be growing crops in those same soils. Arsenic makes it into the plants, etc. So there's a lot of real potential risk that's involved with dealing with this waste in the wrong way.
So you and your team have set out to find a way to make this arsenic waste actually usable. So it's not just a contaminant that gets people sick. Uh,
Yeah.
what's involved in actually turning a concentrated arsenic waste product into something that can be useful in
Yeah.
manufacturing or something else?
Yeah. So I, it's a great question, Lucas. I think the we have to kind of take a step back first, though, because since I was a PhD student, I've been working on arsenic treatment, and it didn't matter. Every scientific conference, every time I was talking to the general public about what I do, the question of what do you do with the waste came up every single time. And at that point, I wasn't the only one working on arsenic treatment, but the community didn't that still really doesn't have a good idea about what to do with this waste. So I've been thinking about it for a really long time, but something like very, I guess, fortuitous for me, because I'm in this kind of research field, has happened with arsenic. And it's that arsenic, the societal value of arsenic is changing almost kind of in real time. So I'll give you an example. In the European Union, every 3 years, there's basically an inventory of materials in the continent that are needed to transition from fossil fuels to clean energy systems. These are the so-called like critical raw materials or critical minerals, critical elements. And these are important elements because they're used in products that are needed for the green transition. 5 years ago, arsenic wasn't classified as a critical raw material, but in 2023, it was classified as a critical raw material in the EU. In the US, the same thing is true. So arsenic is also classified as a critical raw material. But here's the key, is that it's not any or every kind of arsenic compound. It's metallic arsenic. That's the key. So, metallic arsenic in particular is interesting because it's, to me at least, it's one of the precursor materials for making semiconductors. So you can make semiconductors from metallic arsenic. So that gives rise to a lot of its societal value. So that kind of happened in the last 5 years, and that really had what was kind of going on in parallel with the work that we were doing, trying to figure out what to do with this waste. So now all of a sudden we have a goalpost, like we have something to shoot for, metallic arsenic. Now at least there's this compound, there's this material that we can convert, or we can try to convert arsenic in the groundwater treatment waste or the drinking water treatment waste. And if we can get to that metallic arsenic point, we at least know that there are existing markets and things like that. So that was the first step. And to be honest, that had my group and I had nothing to do with that. That's just kind of how society is going. And I kind of attribute that in part because semiconductors, which are, the foundation of modern electronics, the demand for those has really increased in the last years. So now we have this idea that we have arsenic-laden waste that's produced, like you said, every day as a result of an essential service, drinking water treatment. Drinking water treatment's not going to go away. We're going to keep generating this waste. And we want to try to convert that into metallic arsenic. So actually the chemical form of arsenic in the drinking water treatment waste is it's nothing like metallic arsenic. So we really need to kind of think about what kind of chemical reactions need to happen to get from that initial material to the metallic form. Does that make sense?
Yeah, so that's the puzzle then. So you're converting this waste material into something usable, but there actually has to be a chemical transformation that takes place.
Oh, yeah.
Now, I got a C in chemistry when I was in high school. So you might have to walk me through this process,
Yeah.
slowly. But what does the actual chemical process look like
Sure.
in the simplified version that a C student could understand?
Yeah. Maybe I'll get you to maybe I'll start with the actual initial material. So what is the sludge? It's actually arsenic in the +3 oxidation state. So trivalent arsenic is in groundwater. When that's removed from groundwater treatment, the way that it's removed is by forming a chemical bond on the surface of rust, basically. So groundwater treatment is based on arsenic binding to iron oxides or rust. So to get from that material, arsenic bound to the surface of rust or iron 3 oxides, the first thing we need to do is break that bond between arsenic and the iron oxide adsorbent. So to do that, we just use sodium hydroxide. It's a pretty common chemical, and that helps mobilize arsenic or knock arsenic off of the particle. And the reason why we need to do that is if we're going to try to convert arsenic into the metal, we don't want a lot of other elements around that will interfere with that process. So we kind of need to purify arsenic first. So it's already concentrated when you compare it to what's in groundwater, but there's so much iron around now that we have to kind of do a second purification step where we knock arsenic off the particle and separate the particles. And we can just do that by filtering, honestly. So that's the first step, get arsenic off of the particles. And so now arsenic, you have a very concentrated arsenic in water. So chemists say arsenic in solution. So we have a concentrated arsenic-rich solution that's free of iron. And then we add a reductant in there. So that's just a chemical that has a lot of electrons, and it gives the electrons to arsenic. And that's the key reaction, is that you're going from arsenic in the +5 or +3 oxidation state, you're giving it 5 or 3 electrons to convert it to arsenic 0, which is the metal form. And that reductant is called thiourea dioxide, or TDO. It's a sulfur-bearing reductant. But it's actually kind of interesting because this reductant it's used a lot in the textile and garment industry. And in fact, if you Google the name, you'll end up on a bunch of like hobby yarn websites, because like your grandma is like knitting, but she wants to dye her yarn, and this is one of the chemicals you can use. But what makes it super interesting from a chemical perspective is that it becomes very reactive at high pH. And if you remember, we use sodium hydroxide to knock arsenic off the particle, and that works because sodium hydroxide increases the pH. So the same conditions that we generate when we knock arsenic off the particle is exactly where this reductant works the best. So it was a really like kind of I'll tell you, when you do this in the lab, the stuff that you start with is this really brown color because there's so much iron oxide in there, so much rust, and then it ends up kind of turning a really nice like dark gray color. It really feels like some like Harry Potter stuff. It's still amazing to me when we do it in the lab.
This is The Best of Our Knowledge. I'm Lucas Willard. If you are just joining us, I'm speaking with Kees van Genuchten. Kees is a senior researcher from the Geological Survey of Denmark and Greenland and helped develop a new technique to convert arsenic waste into a material that could potentially be used in advanced manufacturing, giving economic value to a notorious waste product. So I know that when it comes to like semiconductors, computer chips, when you look at a semiconductor manufacturing or a chip fab, what they're actually creating is this, they call it a wafer, right? And it's this disc of glossy material that then is then used so you can print a computer circuit onto this very smooth, precise surface. I think I'm getting there. So how do we turn this material then that's been processed with this TDO chemical that a lot of hobbyists are using to dye their yarn, to turn it into a glossy surface and then could potentially be used to print computer chips?
Yeah, that's an excellent question. I can tell you right now that my group is just kind of getting into that space. So right now, when you look at like the market for metallic arsenic, the metallic arsenic that's used to make semiconductors, that process is something that we aren't doing yet, but we're very interested to start doing it. And one of the things that makes the metallic arsenic that we produce, I think, so exciting is that if you purchase metallic arsenic from a kind of like a conventional chemical supplier, the chemical form of metallic arsenic that you get is way different than what we produce. And what I mean by that is that commercial metallic arsenic has a very crystalline structure. So it's I kind of think of it as like a big block. I know that's not something, you don't like look at it and it's a block, but it's got a very crystalline structure. The stuff that we make is very, very, very disordered. So kind of think about glass. Glass has an amorphous structure. Actually, if you go to some of the old cathedrals, you can see that some glass kind of like has like gravity acts on it and it's thicker on the bottom because glass, SiO2 in glass doesn't have a crystalline structure, and so it has different properties than like a crystalline SiO2. So what makes that really interesting is that the amorphous metallic arsenic that we produce, we think it's going to be easier to convert into arsenic-bearing semiconductors, because arsenic-bearing semiconductors, like you said, or like you implied, the atoms in a semiconductor need to be in very specific positions. But if you start with something that's amorphous, I kind of think of it like putty. So if you start with something that where the atoms are a little bit more free to move around, we think that's going to be, eventually it's going to be easier to take that material to get it to form a semiconductor than this crystalline metallic arsenic that you purchase from a chemical supplier. And the difference between a chemical supplier and what we use is like the synthesis procedure. So commercial metallic arsenic is produced in a way different way than what's done with that, than what we've done with the waste. Does that make sense?
It does. And so, because arsenic is so common,
Mm.
and when we're talking about something like semiconductors, could this potentially make semiconductors and advanced technology, electronics, handheld electronics, whatever it is, cheaper? Because arsenic is just found throughout the world as a wastewater uh, treatment byproduct. It's just sort of hanging around.
Yeah, when this project started, there's been the whole idea of converting arsenic into a semiconductor. When this project first started, seemed kind of imaginary. It was like make believe, but we have kind of crossed several kind of like we've crossed a bunch of mountains, I guess, or hills, and we know that we're getting to a place that it's not so make believe anymore. And I remember when we first started to do this, I was talking with a colleague, and they eventually said, so if you're successful, you're basically you're going to take arsenic off of the critical material list. That's what success is going to look like, because you'll be able to produce this all in many, many places around the world. And in fact, I actually think that's fine with me. Like if we're able to take arsenic laden waste that's in the environment and convert it into something that has some kind of value, and that might take arsenic off of the critical raw materials lists, because you won't have the same kind of supply risk anymore. But I think that that's still worth doing, because arsenic has such a kind of nasty impact in the environment. So you're right that it's everywhere. It's easy to find arsenic laden waste. I will say that some waste we've started to do a couple of other experiments now, and some wastes are much easier to convert into metallic arsenic than others. But I think that this really, like this kind of upcycling process, really has the potential to change global metallic arsenic supply chains.
And I just have to ask, what's next for you personally, Case? Obviously, there's a lot to figure out about how this could be brought to scale and the future of this technology and this technique. But what will you be doing personally on this subject moving forward?
Yeah, so I have there's a couple things we're gonna do. We have a project that's going to be run in the next 3 years, where we're partnering with different water utilities in Europe to actually go on site to where some of the arsenic laden waste is produced, and create kind of modular systems on site where we can test upcycling, kind of like as the waste is generated. And the purpose of doing that is to see, when we go from the lab to the field, things always kind of, it's not such a straightforward transition, but we want to see how, like, what kinds of efficiencies we get, what kinds of chemical requirements we have when we do this on a larger scale at a groundwater treatment plant. So that's the first thing. The second thing is that we really started to look hard at other types of arsenic laden waste. So let me give you an example. If you take I'll use the EU as an example because I have those numbers a little bit. I've been thinking about those numbers a little bit more. But if you go across the continent and you convert 100% of all arsenic in groundwater treatment waste to metallic arsenic, that's not going to offset all of the imports of metallic arsenic. It'll be a meaningful fraction, but it's not going to offset all of the imports. And I didn't mention that metallic arsenic is considered a critical raw material in the US and in the EU, in part because the large majority of domestic metallic arsenic consumption comes from imported metallic arsenic. So arsenic-laden waste, if you convert 100% of the arsenic-laden waste from groundwater treatment, you're not going to offset all of the imports. But if you take into consideration that there are other types of arsenic-laden waste from anthropogenic activities, or from human activity, from industrial activity, from mining activities, there's a lot of sources of arsenic-laden waste. And if we think that what we've done with groundwater treatment waste is going to work as well as with other types of arsenic-laden waste. So we're also taking a closer look at what we can do with like heavily contaminated soils or mining waste.
Kees van Genuchten is a senior researcher from the Geological Survey of Denmark and Greenland. His team's research on converting arsenic waste into a useful material with potential applications in advanced manufacturing is published in the journal Science Advances. This is The Best of Our Knowledge. I'm Lucas Willard. If you'd like to tell The Best of Our Knowledge what you think, send us an email at knowledge@wamc.org. You can listen to The Best of Our Knowledge anytime as a podcast, downloadable wherever you get your podcasts. If you want to catch up on past episodes or hear more WAMC National Productions programs on the news, academic study, books, women's issues, the media, and the environment, visit WAMCpodcasts.org. This has been The Best of Our Knowledge, episode 1843. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. The latest on all national productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Lucas Willard.